All right, so talk to me a little bit about if I were to say exponential function, okay? If I were to say exponential function, what does that mean to you now? What do you remember about exponential functions? Monty, what do you remember?
It continues to increase.
Okay, it continues to increase or decrease. Now, I will say this, a linear function continues to increase or decrease as well. So there's an important thing about what Monty says about how it increases or decreases.
Oh, yeah.
So Monty, calling someone, you sort of got the ball rolling in a very good way.
Oh, yeah. Yeah. All right. Well, I'm pretty sure that exponential functions continue to increase at a continually, steeper rate.
Okay, so
I mean, that's what it says, but...
So linear functions increase at a constant rate. Okay, exponential functions increase at an increasing rate, or pick up on Monty's thread.
Decrease at a decreasing rate.
All right, decrease at a decreasing rate. Okay. Thanks very much. Can I get your homework ready?
Oh, can you keep it until tomorrow's table?
Yeah, I guess so. Yes. Yeah.
Can I ask a question?
Sure.
Conceptual.
I'll try.
So, if an exponential function is constantly increasing or constantly increasing at an increasing rate, or decreasing at a decreasing rate, would it eventually stop at a vertical line?
No. And it has to deal with how they increase at an increasing rate. I understand what you're saying. You're saying if it increases at an increasing rate, shouldn't it get steeper and steeper and steeper and steeper and then finally have a vertical asymptote? Certainly if we have rational functions, that's true. But the way an exponential function grows, it's never going to grow such that its growth rate is infinite. Okay? It's going to grow such that the percentage it grows is the same every time, and it's going to grow at a rate that's proportional to how it grew last time. So it's not like an unbounded growth. It doesn't grow more and more and more and more and more in terms of the percentage it grows. It actually grows at a constant percent, and that's going to be a little different about what you're saying. It was a great question. It's not going to have a vertical asymptote. As a matter of fact, can we talk a little bit about what the graph might look like for increasing or decreasing and what the function might look like, and maybe even what a table of values might look like? Sam?
Well, I wasn't going to answer that.
Okay.
Is a linear function an exponential function?
It is not. It's totally different. Okay. So in your mind, you want to separate families of functions, and the linear function is their family, and the exponential function is their family. Go ahead.
I don't understand the difference, because, I understand that a linear function is constant, but can it increase or decrease?
Definitely, and that's exactly what I said to Monty when he said exponential functions are increasing or decreasing. I said, well, so are linear functions. Then Evan said exponential functions increase in increasing. You know what? I think that's better, Evan. Exponential functions increase an increasing amount. Okay? So they get bigger by bigger chunks every time.
Wow.
And they decrease by bigger chunks every time.
Yeah, okay.
Is that better?
Yeah, because
okay.
I thought that it just meant it was...
So we should actually talk about maybe what it looks like, what the formula looks like, and maybe what the values of a table might look like. So I saw some hands before. Who's up? Monty?
Maybe it looks like Jay.
All right, so it would be better if you all had tablet PCs right now, or tablets or something, and you could draw it. But so the with the what? Oh no. So we have an exponential function that's increasing and an exponential function that's decreasing. Okay, so here are two types of exponential functions, and I tried to sort of look like a J a little bit for Monty. It's important, though, as Evan was pointing out, it's not, there's no vertical asymptote here. The further you go out, the bigger it gets. It just keeps getting bigger and bigger and bigger. It doesn't have an asymptote. Exponential functions do have horizontal asymptotes, though. Okay, so in this case, out as we go out this way, it's getting closer and closer to something, and in this case, as we go out to negative infinity, it's getting closer and closer to something. So they do have horizontal asymptotes. What does the equation look like? Sam, do you remember?
X to the n, I think.
X to the n is a power function because x is the base and n is the power. An exponential function actually has the variable as the exponent. So you want to try again?
Alright, 2 to the x.
2 to the x would be an example of an exponential function. Do you remember the general formula for an exponential function from Algebra 2? Yes, no, no.
Like
Keith?
exponential growth.
Yeah.
They're both P naught.
You could definitely use P naught. You could definitely use E. These are all like growth things. So let me, it's definitely something raised to the x. So let me give you a bunch of things that maybe you'll remember. Wake up. Give him a nudge. I was going to ask you to wake him up. He's drifting. You might remember P equals P naught E to the, did you use R or K? Did you use PERT? RT? All right. P equals P naught E to the RT. Some people have seen P naught. Where are the people that have seen P naught? Where are the people who have not? Okay. You may have seen it like y equals AB to the x. Okay. You may have seen it as some combination like y is equal to P sub 0 a to the t. We're going to use them all, right? So the important thing is not recognizing that there's only one way of saying it, is actually appreciating that there are lots of ways of saying it. And actually, if you look, each of these have something very similar in common. They each have a constant out in front. All right, P naught or A. You could call it M. You could call it a whole host of things. Then they each have something raised to the x or to the t. In the first example, it was e to the r. Right? If I had to, I would actually put the e to the r in parentheses, raised to the t. And the second one was b raised to the x. And the third one it was a raised to the t. Now it's really important to understand something. In the second equation, y equals ab to the x. And in the third equation, y equals p naught a to the t. These a's are totally different. They are not the same a. They represent something totally, totally different. So you can't use one equation, solve for a, and then think you could plug it into the other equation. All right, so there's a little bit of confusion there where we use a and what it represents. In each of these cases, the yellow represents what we might call the initial condition. All right, so that's the initial condition. And the blue represents, do you remember what that e to the r, the b, or the a represents? You're making something up, but you're sort of right. It's called the growth factor. All right. Some of you may have even seen, did you do this? Did you do, I'm trying to think of how you may have written it. A times 1 plus r to the x? Did you ever do that? Where in this case, look, we still have our yellow and our blue, right? That's our initial condition, the A in this case, and the turquoise is 1 plus R, and we have 1 plus R is called the growth factor. Oh, I can't spell, sorry. And we had a special name for R. Do you remember what R was? Say it, Michelle. Yeah, it's the growth rate. All right, so the growth rate. And you should remember something like, what determines whether it increases or decreases? How can you look at the growth factor and tell if it's going to be exponential growth or exponential decay? Mo, is that a hand?
Yeah, okay. The egg, if it's positive or negative.
Close, but not quite. Corinne? Closer. Do you want to, like, you're actually getting there. I think saying it's a fraction. What do you mean a fraction? I mean, there are tons. Okay. Okay. So, if A or, alright, if it's less than 1, greater than 0. So we don't just mean a fraction, because you can have a big fraction. You can have like 5.5 as a fraction. So Corinne like actually says it, and then Elizabeth and Keith put the like official terminology, right? Let's see. Let's for this one, let's look at y equals ab to the x. Okay, so we know we're talking about a, b, and x. If oh my gosh, I cannot write. If b is between 0 and 1, then Corinne said we have exponential decay, or it's getting smaller. If b is greater than 1, then we have exponential growth. All right, so you do remember some things. And you can see, as a class, we're doing a great job remembering it. They might not have been things that you remembered by yourself, but as a class, you're remembering it. Michelle?
What is like the little zero for
that little P naught, it's like a subscript, okay? And that subscript, when we say P naught, you can see how we have P in the first one, P equals P naught e to the RT. It's confusing if we would say, usually we use this maybe with like banking or like money, and we would say that the principal is equal to the original principal, what you put in originally. So P naught stands for, represents what you put in at the beginning, or where you started with your growth. And we use the little zero to indicate that's what we're talking about, like the original. Another way of thinking about it is it's P equals P naught e to the R t. And if we wanted to do P of 0, P of 0 would be what would happen if you plugged in 0 for t. What's R times 0?
0.
What's anything to the 0 power? 1 times P naught. Alright, so that's to say that when you plug 0 in, you get P sub 0 out, whatever that value is. So that's an algebraic way of thinking about it. I will wait.
But if anything to the 0,
Is that okay?
yeah, but like,
So e to the 0 is just 1. Anything to the 0 is 1.
if you had a real number in there, how would you figure it
Like, in where? Tell me what a real number and for what?
out? P of 2.
Okay. Now you're asking a question which is a good one, which we would need algebra to do. I agree. When we have 0, Sam says when you have 0 to plug in, that worked out really well. If we plugged in 2 for t, it wouldn't work out so well. And as a matter of fact, if I don't give you the initial condition, if I don't give you what 0 is, then you are actually going to need 2 points. Okay, 1 point won't be enough. All right, so let's take a look at a little bit. Some really good questions, and you're actually pushing me to do more of the chapter than we really need to do today. Do you have any other questions, though, that you want to ask? We're going to get to the answers, like that Sam's asking about and others are asking about. Might just not be today. Is this an okay, start?
Yeah.
Okay. All right, so let's take a look at the classwork. And what we're going to try to do is we're going to try to find the initial conditions and the growth rate or the growth factor. Keep your hands to yourself. The growth factor. All right. And if we can find the initial condition and the growth rate or growth factor, we can put together an exponential function based only on the information that they gave us. All right. So let's take a look. Jennifer, will you read us number 1, please?
The population of a country in 1995 was 53.4 million and growing at a rate of 2.3%. Assuming that the same growth rate continues, write a formula for the population of some years from 1995 and use the formula to predict the population.
All right, so we need to write an equation that represents this model. Now, I need to give you a really important clue or hint. Not just that the chapter is called exponential functions, but if you notice that something's growing at a rate of some percent, that's a huge clue that we're probably talking about exponential. If we said the population's increasing at a steady rate of 10,000 people per year, that's a really good indication that's a linear function, right? If we say people per year, I automatically think people per year, that's a rate of change. Oh, if it's a constant rate of change, that's a linear function. This isn't telling us it's increasing at people per year. This is telling us it's increasing at a percent per year. And as soon as we start talking about percents per year, we're probably talking about an exponential function. All right. Tom, how do you feel about just starting us off? What's the equation for an exponential function? I don't want to plug anything in, just what's the general equation?
I said 1995.
No, don't say any numbers. I don't want any numbers. All I want you to do is go back and look at what we were just writing down and tell me what's the general equation for an exponential function.
Like y equals mx plus b.
All right, not quite. That'd be great for a linear function. I was really not trying to throw you off. Max, help him out a little. Perfect. All right, so if you're thinking linear, y equals mx plus b. If we're thinking exponential, y equals ab to the x. And I want it to be like almost automatic, right? Like, not like we just wrote it in our notes, but like, oh yeah, if someone walks up to you and says, what's an exponential function? You're like, oh yeah, y equals ab to the x. Because don't you do that when someone says, what's a linear function? Y equals mx plus b, right? You should be doing the same with exponential functions now. And there are a lot of different ways of saying it or doing it, but that's definitely one of them. All right. I need to plug in some things for A and B, remembering that A is what and B is what. Miles, thoughts or ideas? You can just tell us if you want what A is or what B is, and we'll find someone to tell us what that's.
So A is 53 million, 53.4 million.
All right, so Miles is going to tell us that it's A is 53.4 million. And what does A in this case represent, Miles? You're absolutely right.
Original.
Okay, the original or the initial amount or condition. People feel all right with that? Yeah, that was good, Miles. All right, Miles, call on someone now to tell us the wrong answer for what B should be. Perfect. Couldn't be more wrong. All right. Danny took 2.3% and plugged that in for B, and that is totally wrong. Thanks, that was awesome. Which makes me think you might know what the right answer is. I'm not going to call on you for the right answer, but it makes me think that if you know what the wrong answer is, you might know what the right one is. Danny, call on someone to tell me what B should be. It's not an easy...
Isn't it like the number of years?
Mm-mm. Find some help.
Point 23?
No, I'm glad. You're still... you know what? I didn't say I want the right answer yet. Still wrong. Oh, and Andrea, another wrong answer?
Would you leave it as
What is it?
nothing?
Oh, come on, I want to know, because everyone wants to know. What's the next wrong answer? 0.023. So here we go. Danny gave us the wrong answer. Elizabeth incorrectly converted it to a decimal, and then Andrea converted it correctly to a decimal. But 0.023 is not. It actually, if you think about it, doesn't make sense. If the population's growing, Corinne. Sam?
I think I'm wrong. Actually,
Courage for the deed.
well, I was going to say 2.3x.
No, good. Nice try, but that's fine. Rafaela? Nope.
I just think it's 23.
I know Corinne knows now. So you want to tell us, Corinne?
No.
Wait, I know.
You got
Point
it.
023 of
It is. It's 1.023.
Oh, but it's
Well,
growing.
remember, we said this back on the last page. You can. But I'm just saying, I'm never going to use just one of them. So, if you remember, B is the same as 1 plus R, right? So if I give you the growth rate, I mean, come on, it's not that hard. You just have to be reminded. The growth factor is 1 plus that rate. And what it actually tells us is, yeah, it's increasing at 102.3%. So you have the original, which is the 1, or the 100%, and the 2.3%, which is the 0.023. Is that all right? You want to ask a question? All right, so a bunch of you put that together very well. Mo and then Sam.
Is X always time then? Or
Okay, so it's not always time for an exponential function. I would say probably 7 out of 10 problems that we're going to do in context, X is going to represent time. Like, so if I'm giving you a problem, it will usually represent, how much money over time, how much growth over time. It could be other things, but I would say probably we're going to run across a lot where X is time. I agree. Sam?
I was going to ask a question where I was thinking the next problem.
Okay, great. So you're saying we should do the next problem. Now, should we finish? Actually, we could finish this off, right? What? Oh, yeah. Okay, so Raphael says, look, if we wanted to do, write a formula, we did that, and use the formula to predict the population in 2005. So Raphael says, that's y of 10. So you have a bunch of ways of doing that. You could just plug in 10. You could put it on your calculator and look at the table. You could trace it. You could actually use your calculator just to do y of 10, right? If I actually go next year, Evan.
What?
Next year, right? What was it, 53.4?
I was grabbing.
Oh, next year, Travis. Next year. Notice you use the caret, the raised to the x, and whenever x is in the exponent, that's a pretty good hint that you have an exponential function. I think I'm just going to go to the home screen and do vars, y vars, y1 of 10, and it tells me the population is going to be around 67 million. Yeah, you don't have to put it in the function. I was putting it there because, look, oftentimes when you're doing a problem, you have more than just one part to answer. So I agree with you, Raphael. In this situation, we only had that one thing to do, so I did a lot more work than you did. to get the same answer. 67 what? Million what? People. Good. All right. You are. So 67,034,379 people. I would say 0.57 is not a person yet. Not yet. Need to wait 6 months or something for that. All right. All right. Number 2. So we have a same situation except a little different. And let's first ask ourselves what's different about it. Depreciating. So Raphael gives us the hint that, oh shoot. Let me try that again. Nope, that's not going to work either. I'm not having any luck with this. Alright. Alright. So we have a car purchased for $21,000. What do we know? As soon as we see depreciating at a percentage, we're thinking exponential. Alright, that's my hope. Alright. Jennifer, give me the general equation of an exponential equation. Okay. And you can pick any of the ones you want. You could pick 1 plus r, you could pick p. I would not pick p. I would not pick p e to the kt or rt yet. But for now we can pick a bunch. Alright. Evan, you want to tell me something we know? A or B?
A would be 2150. 21,500. Alright.
I need something for B, and I'm hoping for a couple wrong answers first.
I've got one.
Alright, Travis, a wrong answer for B?
15.
It's definitely not 15. I totally agree. Alright, I need a couple more wrong ones before I get to the right one. Michelle, another wrong one? 0.15, totally wrong. She converted it to a decimal, but it's still wrong. Okay, but 0.15 is less than 1. Doesn't that make sense? That makes perfect sense. It should be 0.15. No, wrong. Sorry. Monty? Negative 0.15. Even better wrong. Totally. Well, it's going down, so shouldn't it be negative 0.15? You guys are awesome at this. I feel like we could do the wrong answer for a long time. There's not another. Is there really another wrong answer?
33.
Yeah, that's definitely wrong. That is the wrong answer, not even one I was looking for. All right. Monty, call on someone to put this all together to tell us what B should be, given the fact that it's depreciating, as Raphael told us, 15% per year. And all of you that gave us wrong answers actually gave us some insight as to how to answer this one correctly. It does equal 0.85. Why?
Because you subtract the 15% from 1.
Okay, so this really is 1 plus r, except r is equal to, as I guess Monty said, negative 0.15. It's depreciating. When we see depreciate, we think go down. So it's 15% less than 1. And we get 0.85, and that's absolutely correct. Sam, was that your question?
Yeah.
Yeah, okay, good. Tom? You tell me. How'd we get it? Because I just said it. How'd we get it? Go ahead. Ask the question. All right, so if it's depreciating, right, it's going down by a percent from what? What's it start off at? What percent does it start off at? Say again? It starts off at 100%, right? That's what we start. That's the original. So it starts off at 100% of 21,500. What's 100% of 21,500? 21,500. It's going down. It drops from its 100% value. And it drops 15%. And since it drops 15%, that's the same as saying it is 85% of its original value. So instead of saying, right, you could do 21,500 minus 15% times 21,500. Do you agree that this statement represents a decrease of 15%? Watch what I'm going to do algebraically. Factor out 21,500 and I'm left with 1 minus 0.15. Those two statements are the same. 1 minus 0.15 is 0.85. Okay? Monty?
Why would it be 0.01?
Did you miss? It's a blue slip if you miss. There's no throwing trash in the classroom.
Are you serious?
I'm totally serious. Yeah, I mean, I figure how can I give you a blue slip for, like, making a shot? Yep, but if you miss, you're toast. All right. Sorry, Monty.
The last problem it was 0.023.
Yep.
The problem it's just 0.15.
Yeah, so 15%, right? You move the decimal over 2 to 0.15. 2.3%, you move the decimal over 2 places to 0.023. Is that all right? Yeah. All right. Let's see. Let's look at 3. Here we're given a formula. And look, it looks very much like AB to the T. What is the population originally in 1980? Just looking at the formula. Oh, you guys are good at that. All right. And what's the percentage growth rate? Now, I need the wrong answer first. What's the percentage growth rate? What's the wrong answer to that question, Mo?
102%.
102% is definitely wrong. Mo gave me the growth factor. All right, so there's a very small nuance here. The growth factor is 102%. The growth rate is just what it goes up every year. So Mo, call on someone to tell me what the growth rate is looking at that. Yep, awesome. Very good. So the growth rate here is 2%. And let's see if I can write that in. So you all told me, no, that's not what I want, that this was 6.3 million. And you can tell that by looking at there. And this is 2%. And you can tell that by looking there. All right. Hey, nice work today. You guys did a good job with exponentials. Homework tonight is 3-1. And